remind you of where we were. We were talking about the impulse momentum theorem, which is just another version of F net equals ma. We took F net equals ma and massaged it a little bit. F net equals ma sort of applies at every single time it's true, whereas this expression is valid in between some initial time and some final time. And it says, as long as you take all the forces into account, this is always true. The average, if you take the net force and average it between the initial and final times and multiply by the amount of time that elapses, that's called the net impulse. And that's equal to the change in momentum of the object. So we're talking about forces on the left that are being applied to an object, and then this is the change in momentum of the object. Momentum is just object's mass times its velocity, final minus initial. Now, here's a collision where, or at least I'm going to imagine a ball being dropped, pretty bouncy ball like this one, and it's going to go down and bounce up almost at the same speed that it goes down at, right? It doesn't lose too much energy in that bounce. And we want to compare, so this is about the net impulse. In other words, if we add up all the average forces times delta t, how does that compare for the different forces? So here I'm imagining I'm dropping, used to be called a super ball, I just mean a really bouncy rubber ball, onto a table, and let's imagine it doesn't lose any energy. Any real ball wouldn't come up at quite the same speed, but this one we're just taking to be idealized. Right before it's going down at 1 meters per second, right afterwards, perfectly elastic, it goes up at 1 meters per second. During the time of contact with the floor, there are predominantly two forces acting. I'm not going to concern myself with air resistance here. It's contacting the floor is pushing on the ball, right? And gravity's pulling down on the ball, right? So those are two substantial forces. And the question is, from the statement of this, do we have enough information to figure out which force imparts a greater impulse during the contact time? So I mean that very small amount of time, it might be 1/100th of a second that it just quickly bounces off of there. Which force imparts the greater impulse? Weight, the table contact force, and I'm talking about to the ball. Both are equal, or you can't tell from the situation. All right, if you've got a vote, hold it up and let me just see if there's a consensus. I would say there's more C's than anything else. B is slightly less. So either they're both approximately equal or the contact force. Anybody want to voice a strong opinion about their vote? Like what information or what evidence is presented that either they're both about equal or one of them is bigger than the other? Yes, Edward Lee.
The contact force, neither of them are really going in a certain direction. They're just, at that point, they're stopped, so the two forces have to be equal to each other.
Well, yeah, so let's see. Let me try to draw a picture here of, roughly speaking, here's the floor, the ball, here's the ball when it's momentarily stopped. It's sort of squashed on the floor there. And let's draw in the forces, right? So here is the force on the ball from the floor. It's upward from Earth. And here is the weight force. Just say mg. And they're balanced because it's at rest. Is that right? Everything that is momentarily at rest has forces balanced on it. Like that was momentarily at rest when it came, or the forces balanced on it when it momentarily comes to rest up at the top. What forces are on it? My hand's not touching it right now. I've just stopped the movie. Gravity, what else? That's pretty much it. There's not even any air resistance because it's at rest. It has to be moving through the air to have some air resistance. So the forces definitely aren't balanced here. Just because something is momentarily at rest doesn't mean the forces are balanced. Can anybody see an argument for why they would be balanced or wouldn't be balanced? What is the, so the net force would be the sum of these two. What do we know about the net, what the net force determines? From Newton's second law. It determines the acceleration. So does anybody have any intuition about which way it's accelerating at this instant? Like it was going down, and a very small amount of time later, it was going up. So which way is its velocity trending? Upward, right? It went from downward, it trended very strongly in the upward direction, and that's the direction of the acceleration. So at this instant, this thing is accelerating up. You know, it's sort of like the opposite of something at the highest point, right? Before it stopped, it was going up. Right after it stops, going down. So its velocity is trending down at that point, even when it stopped. If the acceleration is up, which of these two forces is bigger? Yeah, the contact force, the force from the floor has to be bigger because, you know, if they balance out, there wouldn't be any acceleration. It's definitely accelerating very strongly up. It changes velocity by a lot in a very tiny amount of time. So that's a huge acceleration. So in this case, let me bring the slide back up. In this case, it's the contact force that is the bigger of the two forces, because you can see from the context that it is accelerating upward. We're going to make an argument now. So I mean, this isn't coincidental that we're talking about this. We're going to make an argument that other forces besides contact forces are usually negligible, momentum theorem, as long as we take initial to be just before a very short collision and final to be just after. In other words, you know, we think of weight forces, they can be pretty substantial, but they have to kind of act over a period of time to really get their effect. Whereas a contact force between two things that are colliding, when there's a very short collision like that, there's a huge force in a short amount of time. And so usually those contact forces really just dominate over all other forces. And so when we apply the impulse momentum theorem, other forces like the weight force, air resistance, if that's relevant, friction forces, they just don't have enough time from just before a quick collision to just after to transfer a meaningful impulse to the object we're talking about. Here's that. Oh, I should have brought up that. I should have seen if I could get that movie going again. Here's the golf ball when it's just, you know, it really does turn into a pancake. It's amazing. So the impulse approximation says that when some objects collide, in this case, we're thinking of something as colliding with the floor, but we could have multiple objects colliding, right? Two balls flying through the air and colliding. And maybe as they're flying through the air and colliding, air resistance is acting on them, and their weight forces from the earth is acting on them. Both of those, if we take initial to be just before a very quick collision and final to be just afterwards, both of those are negligible in terms of the impulse momentum theory. So in a quick collision, lots of forces might be acting. One of those is the contact force. During the very short time of the collision, friction, air drag, gravity forces, they're all much smaller than that contact force between the two objects that are doing the colliding. And so we're often going to ignore those other forces in terms of applying the impulse momentum theorem, okay? The impulse delivered by each of the non-collision contact forces is negligible, as long as the initial time is just before the collision and the final is just after. Gravity can impart a huge impulse if we allow it to act over like 3 seconds. 1/100th of a second compared to those huge contact forces, we can probably throw it away. That's the impulse momentum theorem. The impulse approximation. We're going to ignore all the other non-contact forces. Why do we care about that? Well, we're going to start talking about momentum conservation now in collisions between objects. So we're going to imagine here, we'll generalize this later, but two objects that are going to collide, and they're going to collide while moving along one dimension. You could either imagine that they're moving through outer space, just floating along, and they collide, and they keep on going on their merry way. But for some reason, they don't do this, right? It's not a two-dimensional collision. They happen to bounce back or keep going along the same one-dimensional line. Or hopefully, it hasn't worked out yet, but because another class has been using them, we also have these air tracks that maybe some of you have used in high school before. That's like air hockey. They allow things to move in one dimension without any friction, essentially. So it would be like something's moving in empty space, but for some reason they stay along a straight line. Okay, so let's say I've got a mass m1 and m2. They're initially heading towards each other, or at least in some way. So, you know, one could be going to the left and the other one chasing it even faster, but they're going to collide in some way. We'll call their initial velocities v1 initial, and initial velocity of m2 is v2 initial. And then they collide, and they may not have equal velocities before the collision. They may not have equal velocities after the collision. You know, it depends on the masses, depends on their initial speeds and all that kind of stuff. But we'll call their velocities after the collision, we'll just give them a subscript F for final, V1 final and V2 final. And imagine they're moving in one dimension. So we're going to apply what we know from Newton's third law, right? We know during the collision, no collision is instantaneous. If we imagine those two baseballs coming together, right? If you had it in slow-mo camera, they would come together, no force, no force, no force, and then all of a sudden little force, bigger force, huge force when they're compressed, and then the force gets smaller again. So the force is varying as a function of time. This is true at each instant in time, right? At first, these are small forces, then they're bigger, and then they get small again, right? That's true at each instant in time. If I define the x direction to be essentially along the direction they're going one way or the other, then if this is true for the vectors, the forces are equal and opposite as vectors, then their x components have to be equal and opposite. And if I multiply by delta t, the time, delta t here is supposed to mean the time that they're in contact, the very short time of the collision. And something very subtle happened here. A little bar appeared over these f's. So I've said, if the f's are equal, if their x components are equal at every instant in time, then if I average from some t initial to t final, then those average forces would be the same. And I've just multiplied by delta t on both sides. Why? We're going to apply the impulse momentum theorem. And I've got something that looks like an impulse on both sides, right? We said it was an average force times delta t. And in this case, the delta t is just over a very quick collision time for two kind of mostly rigid objects. Okay, so those two sides are, we might write this as the x component of the impulse of one delivers to two is equal and opposite to the x component of the impulse that two delivers to one. It's just the definition of impulse. Now we're going to apply the impulse approximation. This, I want to apply the impulse momentum theorem, but the impulse momentum theorem talks about the net impulse delivered to an object. And this is just the impulse from the other object on the one object. So in order to change it to the net impulse, I'm going to make the assumption that all those other forces that are acting besides the contact force between the two are negligible. So when I add them in and change it out for the net force, I haven't really added in anything because all the other forces give negligible impulses in that very short amount of time of the collisions. Okay, that's the impulse approximation coming in. And now I can apply the impulse momentum theorem, which says the impulse delivered to two by all the forces acting on it is equal to the change in momentum of two. And that's equal and opposite to the change in momentum of one. Okay. Writing that in terms of final initial, right? Change in momentum of P2's x component is P2 final x minus P2 initial x, and the same thing for the other side. And now let's put all the final stuff on one side and all the initial stuff on the other side. So I'm just taking everything with an F and putting it on the left-hand side, leaving all the I stuff on the right-hand side. What that's saying is if I take the final momentum of object 1 plus the final momentum of object 2, x components, that's equal to the initial momentum of object 1, x component, plus the initial momentum of object 2, x component. A lot of subscripts on there, but they help us keep track of what we're talking about. When something is the same in an initial state and in a final state, we say that quantity is conserved. And so we might say the total momentum, the momentum of each one of the objects may not be conserved, right? One object may come and then, oh, it's all going really slowly afterwards. So it lost a lot of momentum, right? Its m is the same, but its v is much smaller. But the system, this is telling us the momentum of the system of the two objects will be conserved if the impulse approximation is a good approximation. You know, clearly it can't, these objects while they're colliding can't run into a separate brick wall or something like that. That wouldn't be a good use of the impulse approximation, but air resistance and friction and gravity are, oh, they're okay to ignore. So we're going to call that conservation of momentum. Notice we did it for x components here. We could, if things were colliding in multiple dimensions, all of this would go through, and the same thing would be true of y components and z components. So it's true of the vectors too. If we add up the initial momentum vectors of all the things that are colliding, that's equal to the sum of all the final momentum vectors of the things that are colliding. Momentum is conserved, or that's the principle of conservation of momentum. It's not just true for two objects. You could repeat the argument, more complicated for more objects. If we have 10 billiard balls all colliding on a table in some big clunky collision, then the momentum before is approximately equal to the momentum after, where the momentum means the total, adding it up for all of them, okay? And it's not just true for things that maintain their identities. We could have colliding objects. We could also have objects that, you know, come together. Maybe they got Velcro on the edges of them, so they're coming together and they end up sticking together in the final state. I might call that they're coalescing. Still, momentum is conserved when two things come together and stick. Maybe they have the two kinds of Velcro on them. It's also true of the opposite of that. If an object, you know, explodes into three pieces, its momentum before is equal to the total momentum after. So if I have an object sitting in outer space, it blows apart into three pieces. Initially, maybe from my point of view, it was at rest, so I would say it has zero momentum. If you add the three momentum vectors of the pieces as they shoot off, they should add to a zero momentum vector in the final state. So that's kind of interesting. That's conservation of momentum. So sometimes we just say the total final momentum is equal to the total initial momentum, as long as that impulse approximation applies. All right, let's practice with a worksheet problem here. This is not the same. I'm jumping ahead. Keep that worksheet that I handed you on Friday. We will use that this coming Friday when we go back and practice some other problems. But I wanted to try momentum conservation problems. So try one parts A and B1. That sounds kind of confusing, but you'll see what it means when you get the sheet. I'm going to send yours down with this row, Austin. 3, 4, 5. Why don't we do 1A together just to get the flavor of it? And then you can do 1B1, kind of a strange title. So, oh gosh, I just realized I don't think I posted this on the website. That's too bad. Well, maybe I can display the questions for the sake of the Zoom folks. So let me just. I don't think I have any way of displaying them without showing my solution. Well, let's work on 1A together here. So we've got a 3 kilo, I'll show the board in just a second. 3 kilogram hockey puck. I looked up the mass of a hockey puck. It's nowhere near 3 kilograms. They're like, their weight is like 6 ounces-ish, so half a can of Coke or something. 3 kilograms, hefty. I just made this up out of thin air. Moving at 3 meters per second in the plus X direction collides with a 12 kilogram curling stone. I also not a curling person, so I don't know what those, they look pretty massive though. At rest, the two stick together, at least in part A. What's the velocity X component of the pair afterwards? So let's try to draw this. Let me unshare. Oh, I guess I already did unshare the screen. So best to draw a picture always. That's a good idea on an exam too, just so you can visualize. So it says there's some direction we're going to call the plus X direction. And initially there is a hockey puck, which is a really massive hockey puck traveling at 3 meters per second in that direction. And it's going to collide with a 12 kilogram curling stone. Maybe we're looking down from the sky as these things glide on the ice or something like that, right? So this is at rest. And we might call that our initial state. And then in the final state, for some reason, they've stuck together. Maybe there's Velcro, but they're moving as a unit. So you can think of this as an object with mass 15 kilograms, right? And it's moving with some Vx final. I don't need to say 3 or 12. So that's the final state, and we want to find out what it is. So let's write down conservation of X momentum from initial to final. So that means P total X initial equals P total X final. P is MV, right? So I have, just expanding this out, I would have M1 V1 X initial plus M2 times V2 X initial. Maybe I'll call my 1 the 3 and 2 the 12 kilogram. We'll substitute those in. And same thing for final. Now in the final state, I'm going to imagine I've just got one object because there's only one velocity to talk about, I would say. In the final, well, my M1, 3, 12, 15, Vx final. All right, I don't know why I didn't substitute it. What's V1x initial? It's 3. What's V2x initial? It's 0 because initially it's at rest. And I can solve that equation for Vx final. I just have, it's 9/15 I can see, right? Vx final is 9/15 as a number that is 0.6. Notice it's positive as an X component. That makes sense, right? If something's sitting at rest and another thing's coming in and they stick together, they're not going to move back in the other direction. They're going to sort of keep going in that direction. Your brain kind of knows that when momentum is conserved, it looks right. And if it's not conserved, it doesn't look right. You know, if you were in outer space and you saw one asteroid coming towards another asteroid that was sitting at rest from your perspective, and it came in and both of them went in the opposite direction, something would look wrong to your brain. So you kind of have an intuition about this. All right, any questions on that? Try 1B1. The only difference is same initial state, but now they don't stick together in the final state. We're told the 12 kilogram stone ends up moving at 1 meter per second in the X direction. What's the final velocity of the 3 kilogram puck?
What's the final velocity of the stone again?
Oh, sorry. Yeah, I'm forgetting that you guys can't see this. Let me share my screen and go forward. Sorry, I didn't send this to you. So here's 1b1. Final velocity of the stone is +1. It's going 1 meter per second in the plus x direction. What is the final velocity of the puck? I get -1 meter per second. So it's going in the negative x direction at 1 meter per second. Okay. Again, it's crucial, and I probably, it would have been better of me to draw a little diagram on here so I could show what plus x means on here. Anytime you apply conservation of momentum, you need to keep track of components. It's about x components here, and we're told the meaning of plus x above. Sometimes you won't be told the meaning of plus x, and you just got to be sure you make a decision about plus x is the direction the 3 was going initially. It could have been the opposite direction, but you got to be clear about it and stick to it. So in this case, we're just going to apply the same principle, same initial state. So the left-hand side here looks exactly the same. In the right side, the 12 kilogram curling stone is moving with it 1 meter per second in the plus x direction. So that's a +1. And the 3 kilogram puck has an unknown velocity, final velocity x component. So I just call that v3x final for the 3 kilograms. And when you solve for it, I'm assuming you guys agree, -1 meter per second. So in the final state, strangely enough, we've got a massive thing sitting here, a smaller puck coming in, and afterwards that smaller puck bounces back and the curling stone goes forward and they have the same speed. I didn't mean to do that when I set it up, but that's how it came out in this case. Okay, questions on those? That's just the most elementary way of applying conservation of momentum. It's useful, it tells us if you know the initial, you can get the final, as long as you know enough information. Now, when two objects are colliding, there are two unknown final velocities. So you have to be given at least one of them. Or if they stick together, then there's only one and you can solve for it, right? So that's what you're seeing in these two cases. All right. Now, you might think that there's only one way, if two things come together, that they could go apart in the final state, but that's not true. Even if momentum is conserved, there are lots of ways that things could end up in the final state between the 3 kilogram puck and the 12 kilogram stone. It might be easier to see in a different case. So there's an infinite number of final velocities that are consistent with a certain initial state and with momentum conservation. And we're going to think about those now. Let's think of a very simple situation where we've got equal masses. So here I'm saying the two masses are the same, m1 and m1. And just to make it obvious, we're going to make their initial velocities opposite. So same mass, and they're heading towards each other from my perspective at the same speed, right? What could the final state look like? Somebody tell me a particular final state that's possible.
Them both moving at the same speed.
In the opposite direction, yes. And in fact, a particularly simple one is if they're very kind of bouncy balls, right? They're coming in at +1 and -1 x components. They might leave at 1 meter per second too, right? There's like a perfect bounce and they don't lose any energy in that collision. So that's that's pictured here. They leave with the opposite velocities that they came with, right? Each one sort of switches its velocity. And that's not going to be true unless the masses are equal, but That we're going to call an elastic collision because it's what very elastic or springy, bouncy balls would do as they careen off of each other. That in that case, what is that telling us about the final kinetic energy related to the initial kinetic energy? Well, notice the total final kinetic energy is the same as the total initial kinetic energy. And by the total, I mean just you add together the kinetic energies of the two pieces initially and finally, and see if you've lost any. Here we haven't clearly lost any because same masses, same speeds. So that we're going to call an elastic collision. That's only one possibility. What other possibilities are there? Yes. They could stick together. So it might be the case with Velcro. Now, in this case, it would look a little bit strange, but it doesn't look as strange as, the thing where they bounce backwards in that direction. It would be like the two clods of clay. If they're equal masses, opposite velocities, there's not going to be any tendency to move one way or the other afterwards, right? They just stick together like that. It would, it seems like kind of a miracle, but we just don't see things that are that exactly balanced. Their velocities have to be equal and opposite. That's my second case here. You guys are good at guessing the order that I put these in. So we call that case a completely inelastic collision. It's as inelastic as you can get, where elastic means no energy is lost. You might think that this means all the energy is lost. And in fact, in this case, all the energy is lost. But we're going to find out that completely inelastic doesn't mean that all the energy is always lost. In fact, we saw in our case with the case where these stuck together, we would also call this, I'm pointing to the board, so let me unshare the screen just for the sake of the video. In this case, even if these were equal masses, if they're not moving with equal and opposite initial velocities, notice that we would still call this a completely inelastic collision because they stuck together. From somebody's point of view, right? They had some final velocity. If you ask someone who happened to be moving along and watching it as they were moving with it, they would say they ended up at rest. But from our point of view, in this completely inelastic collision, there's some leftover kinetic energy because they're still moving. So completely inelastic doesn't mean you lose all the kinetic energy. That's a beginner's mistake. What it means is you lose as much kinetic energy as possible that is consistent with momentum conservation. In very special cases like this, that might mean that you lose all your kinetic energy. But usually, what it always does mean is the objects stick together. That's where you lose as much kinetic energy as possible, when they stick together like they're covered in Velcro and move as a unit. But unless they had equal and opposite momenta to begin with, they will still have some kinetic energy afterwards. So that's called completely inelastic. It's losing as much kinetic energy as you can while still conserving momentum. Now, there are other cases in between that. It could be that the two objects are coming together equal and opposite velocities, and instead of just sticking together, they bounce off of each other, but bounce apart more slowly. You've seen things do that, right? They come together quickly, and then they move apart more slowly. So they've lost some energy. They've lost kinetic energy in between the initial state and final state, just not as much as they might have. They would have lost more if they stuck together. So this case where they stick together is called completely inelastic. The generic case where you lose some kinetic energy is called inelastic. Completely inelastic is still an inelastic collision. It's just sort of the worst case scenario in terms of losing energy. And you might think that exhausts all the possibilities, but sometimes there's, well, maybe you wouldn't because you've done the reading of the chapter. There's also cases sometimes, although you don't see this very often unless you cook it up yourself, of explosive collisions. That would be like our two objects coming together, maybe slowly, and then when they hit each other, some sort of detonation goes off and they spring apart really quickly. Maybe an explosive gets fired, so they come in slowly and they shoot apart really fast. Or maybe one of them has a little spring bumper that's been compressed, and there's a little clip holding it compressed. And when they come together slowly, it just happens to knock that thing holding it free, and the spring pushes them apart with a lot of kinetic energy in the final state. Both of those would be called explosive collisions. Obviously, anything that is exploding into multiple pieces satisfies that. But in a generic collision, I guess if you rigged up some explosives, you could make things move faster in the final state. You won't encounter that as often as the other ones. Okay, so in all of these cases, we're imagining momentum is conserved, and here what we're concerned with in categorizing them this way is the degree to which kinetic energy is conserved or lost, or possibly gained if it's explosive. All right, let's do an example here. This one's not on the worksheet, which maybe is good since I forgot to email the worksheet or put it on the website. A 2 kilogram cart, again, a cart here could mean just something floating through space, moving at 3 meters per second, collides completely inelastically with a 1 kilogram cart sitting at rest. So this is kind of like the curling stone, except in this case, it's the big one that's moving initially, right? And the one that was at rest was kind of smaller in mass. And they're forced to move along one dimension. It's a frictionless track. Find the final speeds of the 2 carts. So we're just gonna in this case, I was looking for the key word. Completely inelastically is what we need to focus on here. When we say the final speeds of the 2 carts, it makes it sound like there are 2 speeds to find. But if they're stuck together in the final state, there's only 1 speed. They're going to have the same speed in the final state. So completely inelastic means they stick together. So the picture kind of looks like this. This is just like our curling stone problem. I've put an x-axis in there, as I always have to do to apply conservation of momentum, and then I write down the sum of the momenta in the initial state equals the sum of the momenta in the final state. Breaking it down, the 2 kilogram is moving at 3 meters per second initially. The 1 kilogram is at rest initially, and their combined mass, which I don't know why I didn't write that as 3 kilograms there, is moving with some final x velocity component, and we can solve for that, and it's 2 meters per second in this case. So that's just like the curling stone case that we just saw. That's an example of a completely inelastic collision. Questions about that? Okay, let's, I will want to talk about elastic collisions too, but I actually want to introduce the kind of problem that you're going to see in lab, just so you're familiar with it, because in there we're going to be talking about a completely inelastic collision. So a ballistic pendulum is something that was used before the advent of high-speed photography to figure out, how fast the muzzle velocity of a firearm bullet was. It's moving so fast you can't see it, you can't really take data on it, and if you don't have a high-speed camera, that's how we would do it nowadays. This is a technique for finding the initial velocity of this bullet. The technique is you shoot it into a wooden block that is big enough and sturdy enough that the bullet actually gets lodged in it. It doesn't come out the other side. So it's strong enough or sturdy enough to stop the bullet. And of course, what happens afterwards is that the 2 are going to move together. So we can think of it as they're joining together. That's a kind of completely inelastic collision. Okay, so we suspend this block of wood from some strings to the ceiling. The bullet becomes embedded in the block of wood, and the 2 want to keep moving to the right, but the strings constrain them to rock up by a certain distance. The faster the bullet's going, of course, the higher of a height this is going to rock up to, right? If you have a really slow bullet, it won't rock up very high at all. But if you have a really fast bullet or a massive and fast bullet, it'll rock up to quite some height. And the claim is by measuring the height, you can back out what the initial speed of the bullet was. There are several parts to there. So the idea is the initial, and we'll go through a homework problem that you will see in chapter 7. I haven't assigned it yet because I was sort of didn't want anyone to get distracted from the exam coming up. But when this bullet collides with this block, it all happens so fast that this bullet comes to rest before this block really has a chance to move anywhere. So we just consider it an almost instantaneous completely inelastic collision where two things stick together, and right afterwards, the two of them are moving to the right in the image just after the collision. They're moving to the right. Now, they can't move to the right for very long because this thing's on strings, and that causes it to rock up. If I can figure out, if I knew the initial speed of the bullet, and I knew the mass of the block and the bullet, I could use conservation of momentum in inelastic collision to figure out the final velocity of the two stuck together. That would be before it rocks up at all, right? It's still essentially right at this bottom position. And then in the second part of the experiment, it rocks up to a height. And if I can measure that height, there I might be able to use energy conservation techniques. If I knew the initial speed of the bullet, I could figure speed of the two right afterwards, and that would allow me to determine the height. Or conversely, if you write down the equations, if you measure the height, that would allow me to determine the speed of the two right after the collision, which then through conservation momentum would allow me to conclude what the momentum of the bullet was right before the collision. So exactly like it. I mean, maybe it's worth drawing a picture of the kind of thing you're going to see in lab. It's not exactly like this. There is there's a gun. It's not a real gun. It has a spring in it. And there's the same ball we used for that kinematics thing where we were shooting it on the floor. And you're in fact going to shoot it on the floor again for a similar thing, right? So you can cock that spring back and then pull the thing and it shoots that huge ball bearing out. Sitting over here, so there's a little frictionless pivot up there and a rod going down here. And then there's something that has a little cavity in it, and it's got a little thing to catch the ball. So when the ball shoots into it, a little trigger mechanism locks it in there, and so it can't fly out again. And the ball shoots into there, and these two move as a unit. And then this rocks up to a certain height. There's a mechanism through which you can measure the angle. And the claim is, by measuring the angle, we should be able to back out the muzzle velocity of the gun. All right, so let's go back to this homework problem. I know nobody's looked at this yet, but this typically is kind of a confusing homework problem, so it's worth going through together, and then you can try to do your own version when you get to it in the chapter 7 homework. Two small spheres. My version was 432 grams and 604 grams. The smaller one is the one that's going to be dropped. Are suspended from the ceiling at the same point by massless strings of equal length, 10.5 meters. Wow, this is a big one, 10.5 meters. The lighter sphere is pulled aside through an angle of 68 degrees from the vertical and released. First part of a three-part problem asks, with what speed will the lighter mass, M1, hit the heavier mass, M2? In other words, how fast is that 432 gram ball going right before it knocks into the other one? So in this case, we don't have a spring-loaded gun, but we're causing the initial speed just by having some sort of pendulum action. Okay, how would I approach this problem? I'll give you a hint. Momentum's definitely not conserved because this thing had 0 momentum before, and right before it knocks into the other one has quite a bit of momentum, right? So we can't use momentum conservation here. It's not a quick collision, and so we certainly don't expect the impulse approximation to apply. Gravity's doing a lot of work on the way down. Does it remind you of any problems you've seen in chapter 6? Oh, sorry, I should unshare the screen because I'm going to write on the board. You remember that one with the hemispherical bowl and the ice cube that was going from the edge down to the bottom, right? Sort of looked like this. Initial was from rest up here, and we wanted to find that final speed down there. And if you remember, we said the net work done by external forces is equal to delta KE plus delta PE. And we took gravity between this ice cube and Earth to be an internal force, but we took the normal force acting on the block or the ice cube to be external. And why is that not making me worry about that weird normal force when I'm applying W net by external forces equals delta KE plus delta PE. I'm going to take the gravitational force to be internal and the normal force to be external. Anybody remember why I said I wouldn't have to worry about it? The normal force doesn't do any work, so it's going to have to be taken into account over here, but it doesn't do any work because whatever direction it's going, it's always acting perpendicular to its velocity at any time. So it's doing little bits of no work, no work, no work, no work, no work. Okay, so I'm not going to do this whole problem, but this is almost the same thing. Instead of a bowl, I've got a little string attached to this, right? And there's no bowl, but the string tension's just behaving like the normal force on the bowl, right? It's keeping it moving along that circular arc. So let's try to draw, we're going to apply this principle again, and let's draw the system we have here. So I'm going to have to look at the problem, but there's some angle. I'm just going to say 0.4 kilograms. And then there's another one down here waiting to be hit. It was about 0.6 kilograms. I'm just trying to make easy numbers for me so I don't have to write so much stuff. And it was pulled up to, I think, 68 degrees and released from rest. And the question is, what is this one's speed when it's right down at the bottom, just about to hit the other one? Okay, it's like it's riding down a hemispherical bowl. So I'm going to take my system is going to be the 0.4 kilogram mass plus Earth. Gravity is internal. Okay, just to be definite, system 0.4 kilograms plus Earth. Gravity is internal. Tension is external. I know I'm writing in somewhat of a sketchy manner there, but it's enough to remind me of what assumptions I made. And initial is released from rest. Final is just about to hit the other one and at the bottom. Okay. So let's apply that between release from rest and at the bottom, about to strike the other one. I drew these really big so I could put the masses in it, but this one is essentially going to be all the way at the bottom. We're going to imagine they're small enough that it makes it all the way at the bottom before it hits it. Okay, so external forces is tension. Everybody okay with the tension doing zero work in this case because it's pulling always perpendicular to that velocity. That's why I don't worry about putting it outside. But here's the brainless part, 1/2 mv final squared minus 1/2 mv initial squared. Gravitational potential energy for an object near the surface of the Earth is mgy, so that would be mg y final minus y initial. I usually factor it out that way. Anything I can simplify here? The mass cancels out, so I can divide everything by the mass. Anything else I can simplify?
You can get rid of V initial.
V initial is 0. It's in this particular problem, it was released from rest at 68 degrees. I'm just going to, instead of crossing it out, just to make it look simpler. There we go. Okay, so I want to find V final, right? V final is the speed right before it strikes the other one. If I only knew y final minus y initial, I'd be done, right? How can I figure that out from the angle? I forgot to write down the length of the string. It was about 10 meters, we'll say. This is 10 meters. Well, let's see. First of all, y final minus y initial is negative. I want to keep that in mind. It's going down, right? Y final minus y initial is positive when something's going up from Earth, but this thing's coming down. So I expect a negative number. I'm just going to put a minus sign there to remind myself of that. And now all I need to know is how far did it go down? That's what I'm going to put next to the minus sign. Well, to draw it in a picture, that would be like, I want to know this distance here. Now, let me give you a hint. This distance here is also 10 meters in my made up problem there, right? Because when this swings down to the bottom, it will be 10 meters down from the pivot point. Ignore my large spheres. They're supposed to be rather small. Okay, so this is 10 meters. I want to know this. Can anybody see a way to find this? And I can do a little subtraction there. 10 cosine 68. I didn't do the best job of picking my spot here, but from the right triangle, this distance right here is 10 cosine 68 from this right triangle, right? We're just solving for this side of the right triangle. Hypotenuse is 10 cosine 68. So if I do 10 meters minus 10 meters cosine 68, I'm left with what I want. I'm just going to write that as 10 minus 10 cosine 68. All of that needs a minus sign in front of it because this is just how far it went. So that change in y is negative. All right, let's solve for it. This is negative, that's 9.8. I can put it on the other side with the plus sign and then multiply by 2 and then take the square root. And I've got it done here. So let's go back to the slides. Same stuff, right? I've got my assumptions written down, what's initial, what's final. So, subtracting those two things with the extra minus sign in front of it, and then solving for V final. I get 11.34 meters per second. That's not with my made up numbers here. That's the numbers that were in the problem that's shown on the screen. All right. Nothing to do with momentum yet, but that's just like the hemispherical bowl. Now we're ready to conserve momentum. In this particular problem, if you read the fine print, one's coming down and they stick together. And when they stick together, they're moving as a unit right after that. But they stick together really quickly. So they really haven't moved at all. They're just moving together to the right, but they're still essentially at the bottom when they're as a unit. And later on, we're going to worry about it rocking up. What I want to do in this part is just from right before the collision, we know about that now, till right after the collision, when they're moving as a unit to the right. What is that final velocity? So here's part 2 of the problem. After the lighter sphere is released and collides with the heavier sphere at the bottom of the swing, the two spheres immediately bind together. What's the speed of the combined system just after the collision? So let's take, I don't remember what I said before, something like 11.34. Your numbers will be different, but whatever it is. Let's suppose that's the speed of this one right before it hits. Now, I'm going to consider that now for the second part of the problem, just before it hits till just after the two are moving to the right there. I'm going to now consider this to be an initial speed for the next part, right? Because in terms of the momentum conservation, it's initial. So I might call that, to put a better subscript on it, maybe V4, 0.4 kilograms. Initial x component velocity is equal to this. If I call, if we call plus x in that direction, and we're going to do conservation of x momentum in that inelastic collision. So let's write it down. P total x initial equals P total x final. Final means just after they stick together. Initially, I had, and each of these is m times vx. I had 0.4 kilograms times 11.34. That's its initial x momentum. Plus 0.6 kilograms at rest. I didn't really need to write that down, but doesn't hurt anything there. And that's equal to the final total momentum. And there's really only one mass in it, right? The sum of these two. 0.4 plus 0.6, the combined mass moving with the unknown V. I'm just going to call it V final X. And I can solve for that. Let's do that. Here it is. There's the 0 for the other one that's sitting at rest. And let's combine the two masses and solve for V final. 4.73 meters per second. So it was going at a pretty good clip. I think I said, yeah, 11.34. Now it's going much more slowly because it rammed into a wooden block, or in this case, another ball that's quite a bit heavier. So that slowed it down. All right, finally, part 3, what is the maximum angle of deflection of the two bound objects? Answer in units of degrees. So we want an angle, a final angle. How do you think we might approach this one? Got to keep an eye on the time here. Can't see it. 3:58. Wow, we better hurry up. Well, it's sort of like we're on the hemispherical bowl, right? Now I got the combined object and it's riding up the other side. So we're going to use conservation of, well, not conservation of energy, but we can use our work kinetic energy theorem that says W net by external is equal to delta KE plus delta PE. Same system as before. The combined mass plus Earth, gravity is internal, tension is external, and that tension doesn't do any work. Now I go to sleep for a second. We'll fill in the details in just a second. Plus mg y final minus y initial. And notice this is our thing we want to find. How high does it go up? Oh, no, actually, we don't want to do that. We want to find the angle, but we'll solve for this first. Let's first solve for delta y. And then we'll figure out what the angle is. Well, let's see. In this case, isn't V final 0? It's coming to rest. I'm going to take initial to be just after they stick together, and final is they've rocked up to rest. So V final is 0. V initial is what we just found up here. It was the 4 point something meters per second, right? I could cancel the m's again, and I could solve for delta y. I'm being a little bit sketchy because I know we're just about out of time. So it's the same picture on the other side. And now the question is, what's that angle? So let me redraw it over here. The two combined things are over here, stuck together. And we want to know this angle theta. And what we've just found out is that this distance is some delta y, positive in this case. How can I convert that into an angle? Well, it's kind of the reverse as before. I'm not going to belabor it too much because again, we're almost out of time. This was about 10 meters. Now, this is also 10 meters here. This right here is 10 times the cosine of theta. And therefore, delta y is equal to 10 minus 10 cosine theta. So I'm going to have my known delta y equals 10 minus 10 cosine theta. I know this, and therefore I can solve for cosine theta and take the inverse cosine. You want it in degrees, so make sure you're in degree mode in your calculator. All right, good enough